All right, so let's review our semaphore thing from last time. It wasn't doing too much, but the code actually does work. Just to show it to you real quick here. GCC pthread. So now I'm on cloud 9. It worked as is, and then we'll talk about it. What do I call it? Semtest. All right, so is there a way to? It doesn't really help. Whatever. All right, so we. Oh, I must have erased it by. Let me run it one more time. So we have initial one entered, and then it just exited, and then the second one came in, entered, and then it exited after, what is it, 4 seconds? So if you remember from the code from last time, our thread here, we come in, we wait for the semaphore, we enter, we sleep for 4 seconds. Now what is a semaphore? What, if you had to concisely define a semaphore, what would you say? Like on a quiz or something. Yeah, it's kind of a special purpose integer, or maybe if you had to be really concise, an atomic integer, something like that. So an integer whose increment and decrement works as if it was atomic in one CPU cycle. Okay? So as soon as we do sem wait here, we are trying to decrement that integer. Okay? And when we finally can decrement it, that is atomic, or as if it was atomic. That's when we now can safely, I mean, even though printing is an expensive task, we can go ahead and safely print, because as long as we haven't relinquished that, that's our section of code. Okay, that's the critical section. Right? Nobody else can get in there. Well, in an example where we're using a 0-1 semaphore, right? Because technically a semaphore being an integer, we want to give 5 people access to the same resource at once, but no more than 5. This would work. Okay, but the point is that in a 0-1 semaphore, as soon as we're let past this line, as soon as that line stops blocking, that's our resource until we give it back right here. Make sense? So we just printed out entered, then we went to sleep for 4 seconds, then we printed out just exiting. So here's our original entered. 4 seconds later, well, if you remember from down here, we had a couple of threads. Here, this was my code I had for some testing, but I don't use it anywhere in there. So I had my first thread get created here, which called our thread function. Then I went to sleep for 2 seconds. Then I created my second thread. So the first thread came in here, he grabbed the resource, he's sleeping for 4 seconds. About 2 seconds into his slumber is when the other guy gets created, and he tries to decrement the guy here and is unsuccessful. That line blocks him. All right, so we entered. This guy's now sleeping for 4 seconds. In the middle of that 4 seconds, this guy here, actually, where's my start thing? Entered. Why did it print entered twice? Is that a scrolling thing down here? Let's just assume that's the case, because it should be fine. All right, so this guy was trying to enter for 2 seconds now. He was waiting for this guy to finally exit. And as soon as that guy exited and he did a post, he incremented the atomic integer, the semaphore. This guy was then finally able to decrement it, which allowed him past this line. So this line stopped blocking. He came in and said entered. And then he slept for his 4 seconds, and then he said just exiting. That makes sense? I think the issue we had, if you remember on the Mac side, we were getting all these warnings, right? Oh, this is actually a different kind of warning. But point is, we had warnings coming in about semaphores. And so we ran it anyways, right? Well, the semaphore functions weren't actually doing what they were supposed to do. They were blocking, but we weren't. They were deprecated. They were deprecated functions that no longer functioned the way they were supposed to function. They still blocked, okay, but they didn't. They blocked based on a random amount of time. They didn't block based on actual interprocess communication stuff. Okay, so that has to be something with Apple's library. I'm sure there's an equivalent to it. We don't need to go and figure that out. Code as is worked on Linux. So whatever it is, there's going to be an equivalent to the OpenBSD semaphore post and init, or rather post and wait functions that will work on the Mac without warning, and they would actually function the same way. But we got a pretty good feel for how semaphores work now. Okay, so let me go into Keynote here. Remind me, what's a queue? CSC450. What's a queue?
It's a collection, data collection, or things get added at the end and taken off from the front.
Okay, first out, first in, first out. It's a line. Okay, so things get n-queued into the end of the queue, which I just hate that function name, right? Okay, and then things get d-queued, which always makes me hungry from the front of it. Get it? DQ. Yeah. Ha, 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 ha. All right, so NQ and DQ, but it's a first in, first out queue or a line, okay? That's what that data structure is. Well, we have something in interprocess communication known as a message queue. All right, so a message queue is kind of a global queue that's available in the operating system that is can be open for reading and writing or read-only, all sorts of stuff like that. And effectively, whenever somebody checks the message queue, it grabs the next message. All right, so we don't get notified when something changes in the message queue, but the next message is then advertised to us. So when we say message queue, new messages, it grabs the front of the queue. Even if there's 300 messages in there, I get the very next one. Okay, and if I want to keep getting things, I can keep reading until I come up empty, until the number of bytes I read is 0. So it's kind of like reading from a file, except file we're looking for specifically end of file, as opposed to we could just keep reading from a file 1 byte at a time until we can't write, until we read no bytes. Okay, so that's what a message queue is. So this guy, so we're going to say reading from a message queue is a blocking function. Because if we read from a message queue that has nothing in it, it blocks until something is there. Okay? So that allows us not to have to worry about synchronizing two things. We can have something try to read from something that's nothing there, and he just sits there and holds until something finally gets written here, and then he retrieves it. All right? So it's a blocking function. Now I have some sample code. We have a client and a server model set up, and what we're trying to mimic here is this idea that you have a server who's handing out unique IDs to clients. Okay? So your client 1, your client 2, your client 3, so on and so forth, but making sure that clients always get unique IDs, that no two clients get the same ID. Make sense? All right. So without going any farther into this, how might you accomplish this using exactly only what we've learned so far in this class? How might you architect a solution where you're handing out unique identifiers to multiple clients or multiple threads, we can say? Should actually be a pretty easy solution.
Have an integer you implement every time a new thread.
Okay, and when you increment that integer, where do you put it?
Share.
Well, we need to make sure that 2 different threads don't read from that integer at the same time, right? So what kind of animal do we have that can lock down a resource so that only one guy is accessing it at a single point in time? Semaphore, right? So we can have a semaphore that locks the door and opens the door. And in the middle is when the thread says, the next guy is my ID. So he grabs his ID, then he increments that number. Doesn't have to do any sort of special increment. He could take his time. He could wait for 4 days in there if the next guy's going to be ticked. But, when he's in the critical section, that's his code. So he can get his ID from the integer and then increment the integer so that the next guy through can go and grab his ID, right? So a pretty simple thing to do if that's all we're handing off, right? Now, the reason I'm using this example, A, it was in line with the example I brought in from online, but also B, it's an easy thing to understand, right? Handing out unique IDs, this isn't rocket science type stuff. Okay, so we're going to create a server and a client for this. And as part of this, I'm also going to show you, and you may have been doing it all along, but whenever we do our compile, we're always getting an a.out. Well, since we're having a server and a client, then our a.out will be whichever one we compiled most recently. Probably don't want that, right? We probably want a server and a client, separate executables. So we're going to use the -o flag on GCC to allow us to uniquely name our output file, rather than just stick with a.out and say that's good. All right. So let's go in. I already have Cloud9 opened here. And I'm going to look at the message queue server thing here. All right, so this guy has a whole bunch of stuff in it that we're bringing in. Now, one thing I did do is I showed you the GCC command for compiling this. Actually, if you want to add to this -o server, that'll give you an output file named server instead of a.out. Okay, so the -o flag is the output flag. Just out of curiosity, if you're ever wondering, so if you have a command like GCC, a lot of times you could just actually press GCC and press enter and it might, I thought it was going to give me a list of the help files for this. You can do GCC-H. There we go. So you got a couple of options here. So I just kind of showed you the naming conventions for a lot of Unix commands. So sometimes you could type in a command, press enter, and if you didn't use it right, it'll give you a list of acceptable uses for it. GCC isn't one of them. The next thing maybe to try is do GCC, then various Unix tools, they use those command line arguments. That's where those things are from. The argv, the int pointer argc, and char pointer argv, those guys. That's where those command line argument things really came from, is this world. So we would provide it with maybe a command line argument like -h for help. Fairly common that this guy would work. So press enter. Not this guy. Our next guess would be --h might work, but I would not expect it to work. No. So --help. Okay, so this is another kind of common naming convention for programs that will give you acceptable use of this guy. All right, we see that. Say this again.
Dash is always meant for full word.
Yeah, but you don't have to. That happens to be the naming convention. It doesn't have. Your full word could be one character.
It's like a standard.
Yeah, right. Yeah, all these are naming conventions, not rules. All right. Now notice that it gave me a big wall of stuff here, right? So if I want to, instead of it just dumping to the screen, if I want to read this all at once, so this is kind of Unix crash course stuff, I can take the output of that and I can pipe it to more, which is another program, and more will show it to me one screen at a time. There's also a kind of an equivalent program to more called less, which will do kind of the same thing. But if I do that, it shows me the first page, so usage, blah, blah, blah. I can look at some of the options. I can press spacebar, keep going down, so I can read it one page at a time. All right, similarly, if I want to put it into a file somewhere, I can go ahead and redirect the output into a file so I can read it later, that kind of stuff. All right, but in any case, for our perspective, if you want to know how a command works, you can do GCC-help or GCC or whatever the command is -h, and that should get you somewhere. Also, sometimes they also include a manual page with the install. So if you do man space GCC, yep, they didn't. So no manual page with this one. So you're stuck with whatever their command line interface
You
is.
need to install the man itself, the manual.
There's a package for GCC that's the man page.
The man itself, I think. And then we'll download it, like we'll update all the manuals that wherever you install it.
Oh, but I mean,
Maybe, yeah, manual works himself, but there is also a supported package.
I gotcha. So somewhere in there's a repository of manual pages that you can update or something like that. Is it built into the man page? No, whatever. Okay, so just some crash course-y type stuff there. So in any case, let's go through this message queue server. But we do need to link in. This is something called RT, real-time library. All right, so similar to us linking in pthreads before, we're linking in the real-time library, which is what message queues use. So that is required for message queues to work. All right, so we're getting a lot of our old stuff that we got before. Here's our message queue stuff here. All right, so now we're defining. So these guys, what's this kind of thing called? What does this produce for me? What's the C terminology for what that line produces? Go ahead.
Constant?
It ultimately acts like a constant, but that's not what it's called. And actually, it doesn't act like a constant. Macro, yeah. And it doesn't act like a constant. This is faster than constants. So constants would be variables that cannot change, right? But they're still resolved at runtime. Macros are resolved at compile time. So what this does is any place in my code where I've used the word server underscore queue underscore name just like that, at compile time, it replaces that with that as a literal, not as a variable. So it doesn't need to be resolved during runtime. Make sense? So macros equals speed. All right, so I'm defining a whole bunch of macros here, whatever. So this is the name of my server queue, so SP example server, whatever. Just this is a unique name that you're going to have for your queue, just whatever it is. The clients are going to have to know about this guy. So pick a name that you're willing to hand out or something like that. So we're naming a line. All right, so we're thinking about this as like we're waiting in line at McDonald's. So up in our operating system, we're creating a queue, we're creating a line and saying, this guy has this name, so when I tell people to write to this, they know which line to get into. Okay? Max messages on the queue, max message size, buffer size is max message size plus 10. I guess that's to give you some spillover. I don't know why they had to specifically give it 10. A /0 would have been enough, but whatever. This is some information dealing with the constraints of your queue that we're probably going to be using to construct our queue. Okay? So then we have our normal main. Now, this MQD underscore T, what kind of animal do you think that is? Struct. Underscore T tells us it's probably a struct. All right, so we're creating two variables of that type, QD server and a QD client. All right. Then we're going to have our little counter here. So this is the kind of the integer we talked about a few minutes that we were going to protect with the semaphore. So that just happens to be a long, which seems to be, well, I guess a long would be beneficial because the max number of messages they allow at once is 10. But technically you can have an infinite number of messages that will ever come through there. So potentially you can run out of size of int. But you could also potentially run out of size of long. But whatever. All right, so they're going to go ahead and keep our token number at 1. This is the unique IDs we're handing out. So your token 1, your token 2, your token 3, so on and so forth, making sure that we always give you unique tokens. All right. Now, at the end here, I'm going to ask you, after we kind of go through this, I'm going to ask why we did not have to use a semaphore here. All right, because we already came up with a solution of this for this that wasn't really that bad, right? Semaphore solution. Just lock down who can change this integer and when, and done, right? So I'm going to ask the question why we did not have to use a semaphore here, and then well, I'll leave it at that. So kind of keep that in mind as we're walking through this. Okay? So server's going to print out, hello world, I'm running, blah, blah, blah. Then we have this struct called a MQ underscore attribute. And we're going to fill this thing up with some stuff. So max messages, message size. So this is kind of like what we did with sockets. Give the information about what this message queue is. Okay? So we have our attributes. Next thing we're going to do is we're going to establish that queue. So we're going to name our line up in the operating system. So we're going to do an MQ open. Here's that server queue name. So this is really the macro that we have here. This guy will get replaced at compile time prior to runtime. That sounds like a very interesting question that might show up on a final. What's the difference between a macro and a constant? I really like that idea. Love that idea. That's going to make the macro versus constant. What's the difference again?
Runtime and compile time.
So constants are resolved at runtime. So we're going to say slower. Macros are, we're going to say replaced. We could also say resolved, kind of the thing, same thing, at compile time. We'll call this faster. Or at least faster execution. He still has to take the time to go through and replace it, but that's all happening one time ever at compile time.
So why use constant at all?
That's a reasonable question. Why use constant at all in C? I don't know that you would. Let me think. It's possible. Oh. I'm about 97% sure on this answer. So I'm going to give myself 3% wiggle room here. Pretty sure it's right. I think a define only works inside of an individual file, where you could have a constant that actually lives inside of another file that you are including in this file, and the define I don't think would carry through then. So if you have, like, for instance, you want to have a constant for pi, math library I'm sure has a constant for pi, you could then include that. But even as I say that, I'm thinking if you included in your .h a define from there for pi, wouldn't that work? I think it would. I don't know the answer to that. Yeah, why would you in C? Well, first of all, in a language like Java, we don't have macros. But in C, we do have constants. Well, at least in C++, we have constants. We'll see, we have constants. Yeah. I'm sure there's a good answer. I don't know it. So, I don't know. That's, somebody wants to look that up and enlighten us next class. That could be a very interesting thing. But macros tend to be the C way of doing things, but I think that is there is probably a downside to macros maybe for the executable size. Maybe the executable size changes or something like that. Okay. So we'll go ahead and open up our queue. The queue that has that name, we're going to be opening it up for read-only as well as creating it. All right, because the server is going to read from it saying who's asking me for their unique ID, but he also needs to be able to initially create it if this is the first time it's being created. All right. Anybody remember what we called this little single pipe between these two? When I say this guy single piped with this guy, what's that called? It is a bitwise OR, but this technique of taking two options and doing a bitwise OR between them, what's that concept called? I think I've mentioned this in class. Masking? Have I mentioned that? Yeah, so masking is used with option flags. Let's call it option flags to bitwise or flags together, producing a new flag that contains the meaning of the initial 2, let's say. So it allows you to pass multiple flag values in a single parameter, right? Otherwise, you might have to give it like a list of options, something like that. But instead, I can pass in a single parameter that is 9 different options all masked together, producing that unique output that is the only way you can get this output is with these exact options. Make sense? It's almost like an encryption type thing, except there isn't a security aspect associated with it. It just, you got these 2 things, bitwise OR them together, you get this result. This result means whatever these 2 things meant together. And that's called masking. All right, but in any case, we will establish our queue, storing the pointer to it inside of our QD server, which was one of our MQD pointer or MQD structs. Okay, and this is just the error checking for that guy. Then we're going to have a couple of buffers. So these are going to be things for strings. Okay, and we probably look ahead and we think that these are probably things, when we see the word buffer, these are probably things that we pass into functions in C, because C kind of has this, typical convention in C is that when you need a string to be written, you pass it into a function as a parameter. It then changes that string at its address. Because most functions in C do what? What do they return? Why can't we just return the value that this message should be? We can only return one type in C. What do most functions in C return?
Integers.
Yeah, usually an integer. And what does that integer represent?
Represents whether it worked or whether it hadn't.
Yeah, error messages, whether, did it screw up? How did it screw up? Those types of things. So that's why pretty often you're seeing us, when we make calls to these things, we're wrapping it inside of an if. Because first of all, Booleans are zeros or ones, or zeros or non-zeros officially in C. So to find out if this worked, we are looking at what did this guy ultimately return. This guy ultimately returned a number that said whether or not it worked, but it maybe had made some changes to these attributes or something like that if it happened to need those. In this case, it doesn't look like any changes would actually be made. All right, but certainly down here, if we look at it in this next thing, so we have our couple of strings. So these are things built for holding strings coming in or out. This is a infinite loop, right? While true, so while 1. Then we're going to try to receive. So the server establishes his queue, and then he tries to read from the queue, and that's a blocking line. So when he tries to read from that queue, until there's actually something there, he can't read from it. All right, so what queue is he reading from? This queue, that is the one he either created or reopened if it had already created. So this guy does persist between runs of the application. All right, so he'll get a pointer to that guy. And then what he wants to do is when he reads something in, and here's the example of what we just talked about, he's passing in this in buffer, and that guy will get filled up with whatever it read in from the first element of the queue. Make sense? That's the information we read in. What ultimately gets returned by MQReceive is whether or not this worked. True or false, whether it worked. That make sense? All right. That kind of question would be a good one on like a quiz or something too. All right, so ultimately, assuming we didn't have an error here, blah, 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 after this line finally executes, when it stops blocking, that means at least one client has written something to the queue. We have read from that queue, and what we read in is stored inside of this thing called in buffer. All right? So server just spits out, I received something, blah, blah, blah. All right, so now he's going to send a message to the client. Now let's pause this here for a second, and let's go and look at how the client sends messages to the server. See how these two, because ultimately we couldn't get past this line until somebody wrote something to this buffer. All right, so we'll pick up here on line 53. So we go over to the client here. All right, client does a lot of the same stuff. Notice we have the server queue name. That guy matches the other one. All right, so we need to make sure we're talking about the same line up there in the operating system, right? All right, because if I'm going to write a message there, I expect the server to read it from there. We need to make sure we're writing and reading from the same place. All right, all this other stuff is kind of the same junk. All right, so the client is going to have their own queue name. All right, and you'll see how they're going to use this here in a second. So then we go ahead and we have our queue server and our client queue that we're going to have for our couple of queue descriptors. All right, so sprintf, have we actually seen an sprintf at this point? We've built some strings by hand. Sprintf is pretty handy for us. So what does printf do? What does just the printf function do? Nothing new. Just don't even look at the screen. Just what does printf do? Displays crap to the screen. That's what printf does. Now, what do you think sprintf does? What does S probably stand for? String. So this allows me, instead of printing it to the screen, I can print to a string. Now you might say, well, why would I ever want to print to a string? What's one of the unique and, let's call it, helpful features of printf? What's nice about printf?
String formatting.
Yeah, the formatting stuff. %D, %S, %P. I can write a string and put all those little placeholders in there, and it just magically builds the thing for me, right? Now, historically, we've done that to spit it out to the monitor. But now I can put it into a string. That make sense? What string am I putting it into? The guy I passed in right here. So another example of us passing in effectively a buffer into a function and having the function update that buffer. So what does sprintf do? When it's done running, this guy right here, make sure you give him enough memory to hold what he needs to hold, will hold this string followed by a dash followed by some integer. What integer? Here's a function built into Linux operating system, so it's written in C, called getPID. This would be the process ID of this client program. Now, why do you think I'm getting the process ID? Because ultimately, I'm putting this inside of client queue name. Yeah, process IDs are guaranteed to be unique on an operating system. You can't have more than one process with the same process ID, otherwise they're the same process. Right, so presuming these are all running on the same operating system, same exact operating system, not both Linux, but the same computer, each client that you run will be guaranteed to have a different process ID. So this guy is going to name his client queue SP example client dash whatever his unique process ID is. So each client will get their own unique queue. All right, that makes sense? All right, so that's what this line does. This client says, I'm going to have a queue with a name that nobody else has. I'm going to use sprintf to create it to write to a string conveniently. All right, this is a handy function, sprintf. All right, then we do our whole attribute stuff, just like the other one. All right, then the client is going to open his own queue. So this is the whole read-only create, just like we did with the server. What's this called again? Masking. Okay, so we're masking our options there to make this guy read-only and create, so this guy can create it. Now, what is interesting here is I'm not sure what the kill time is for a queue. And there probably is also a maximum number of queues that can exist in the system at once. So a potential attack on an operating system would then be write a program that has a infinite loop that just keeps creating new queue names, unique queue names. Right? Well, it's an attack. It's meant to make the operating system not act right afterwards. So if you have, let's just pick a number. Let's say that an operating system can have up to 65,536 unique queues at any point in time. I can take all of those for my single client. Now no other program can use message queues. There's probably a facility for protecting against that, but if you think like let's call it an earlier day Linux hacker or something like that, those are the kinds of exploits that, you would look like, how can I be a jerk type thing. Okay? I'm not recommending this. I'm just saying that, as you're reading through code, sometimes it's helpful to just think of the ramifications of various lines. Okay? All right, so client's opening up his own queue. We'll see how he uses it here shortly. All right, then the client will go ahead and open up the server's queue, but notice that he's opening it up for write only. So we're not doing any masking here. We're getting the result. The result of this will be the same, something that looks just like the result of a mask, but he only wants permission to write to the server's queue. He can never read from it. That's the server's thing, but he should just be able to write to it. Okay? So now he has access to read from his queue and write to the server's queue. Make sense? So he's kind of created a two-way communication using two separate queues. All right, then we have our in buffer. So this is going to be, probably something we pass in, and the string gets filled up with some stuff. Now the client is going to ask the server for a token. All right, and this program here just says, press enter, and we're going to press enter to have it go somewhere. Why? Right here, this fgetS, this gets a string from the user, and we don't care what string we get. It's reading something in from standard input. All right, so we don't have to press enter if we don't want to. You can press G if you wanted to. So it's just reading something in that will, because this line blocks until the user types something for it to read in that string. All right, so now we're in here. So when we read something from the user, the client presses enter. We come in here. What do? We try to send to the server's message queue. And the information we're putting into the server's queue is the name of our queue. That make sense? I'm letting the server know how to reach me. So I'm giving him my phone number, if you will. But I'm giving my unique queue name. Okay? And here's the length of that guy, blah, blah, blah. All right, so I'm adding a message to the end of the server's queue that will ultimately do that. Then I'm expecting a response from the server. Okay, so let's pause this. Go back to where we were here. The server just received the name of a client queue, right? That's what he got right here inside of InBuffer. So when this line finishes blocking, what he has, and when he says message received, inside of InBuffer is the name of a queue which leads to a client that a client is going to be reading from. Okay, so we'll send the reply message to the client. So he's going to go ahead and open the client's queue for writing only. So the server is saying, okay, I'm going to establish a connection to this client. He gave me his name. And then what am I going to do? I'm going to do an sprintf. So I'm going to fill up outBuffer with a token number. And remember, a token number was our long from up above. All right, so this is a long decimal. That's what LD stands for. Percent LD is long decimal, as opposed to percent D for just an integer. All right, but write in the same kind of value. So now he has outBuffer, which is just the string he intends to write back to the client. So now he's going to do a send to the client, passing it outBuffer, passing it the length of the outBuffer, so the client will receive his unique ID. Make sense? Server gets the request from the client with the client's phone number, his queue name. Server then opens up that queue name for writing, writes the ID for that guy to that queue, presuming that the client's going to read from it, right? And then the server said, hey, I finished responding. He goes ahead and increments token number by 1. So the next client that he reads from, he can send the next, now you're ID 1, ID 2, ID 3, so on and so forth. All right, and then in here, we should see what? The client should read from their queue their token number, their identifier from the server. All right, so here's the client reading from their own queue. They're reading it into a string called inBuffer. Afterwards, the client's printing out token received from the server. Here's the %s, he's getting a string back from the server, and here's inBuffer. That's the server gave him his unique identifier from the server's perspective. All right. And we can, this effectively stays in an infinite loop, right? Because it just spins back up and waits for the person to hit enter again, which makes that client then connect to the server again, pretending he's a brand new client, saying, give me a token. Server then hands him the next token. All right. What does the server do here? Server goes back up and listens for another request for a token. All right, and down here at the bottom, when we exit out of the reading stuff, we'll close our queue and unlink the queue. So that's just bookkeeping stuff. So then my question here that I warned you about is, why do we not need to protect token number with a semaphore?
Only the server is on actually control this.
That's true, but you do have multiple clients that might all request a token number at the same time.
We don't.
So it has to do with the nature of this receive here. This guy blocks, and when he receives something, he only receives a single message. If there's 400 messages in there, he gets message 1. He won't get message 2 until he spins back around in this loop and grabs message 2. So even though you may have many clients all requesting tokens at the same time, you only actually ever have one token to hand out at a time. So you don't need to worry about handing out the same token more than once because, as you pointed out, only the server has access to that variable. So we're effectively building in kind of the semaphore type practice, semaphore type functionality rather, using queues instead of using a semaphore because we're making them wait in line.
Because you also separated the server from the client from
Yep. But the same thing would be true if we didn't separate them. We could have threads that are writing to a queue, right? And if 20 threads all write to the same queue, the server's still only going to read from one of those threads at a time. That make sense? So we can effectively replace semaphores with message queues because message queues have built into it that fact that only one message gets read at a time. What's the advantage of that over a semaphore? Well, they both act like they're atomic. We don't necessarily have to worry about how it's implemented under the hood. Semaphores can't pass any information, right? Semaphores just let us dive into a critical section of code and protect it. Whereas a message queue allows the client to send requests. You could have this one client from the in the message queue send 20 different requests. Couldn't you? I mean, we could have hey, you wanna know your ID? Fine. You want to know your last name? Fine. You want to know the current account balance in your bank account? Fine. So depending on what they're asking for, and that message they pass them, that could be complex, right? We're passing them a string. Well, it doesn't have to be a string. They're passing them some memory. But you could format that string however you want and then use scanf, which we haven't done yet, to piece those things out. So you can have pretty complex requests then. Okay, so we're going to return to message queues here within a couple of classes, but I want to think about linked lists for a second. That way we have something to implement for our homework. What's a linked list?
It's a list for each item of the next item on the list.
Okay, so it's an arbitrary array that isn't necessarily implemented in contiguous memory. So each individual element of our list must know where the next element in the list lives in memory. Okay, so when we've implemented something like this in Java, what have the individual nodes been? They've been objects, right? Well, now we're in C. We don't have a such thing as objects. So what might a node be in our world here? Struct. Struct that holds on to maybe a payload and the pointer to the next node. That makes sense? So what we want to do is we want to implement a linked list capable of holding ints in C. Implement the add front and add end functions. Actually, let's do this. Let's implement add front and get front. Let's just do the two easiest functions just to get the syntax down. Then we'll add to it from there. Sound good? So for Wednesday, a struct-based linked list of ints where we have the functions add front and get front. Now you can implement this however you want inside of a single file. What we're going to look at on Wednesday is what if I kind of want to put that linked list implementation in another file and then bring it into my code. If you want to go ahead and look ahead and how to do that, you can. Otherwise, don't worry about it. Just get this functionality working. Write your functions, whatever. Questions, comments, concerns, bribes? All right, I will see everybody on Wednesday. If you're at the hackathon, is anybody going to? Oh yeah, a couple people were at the hackathon. Good job. We got some prizes. We got some food. We had some fun. Some people won prizes.
Some people.
Yeah, I mean, I just had too much stuff I came home with.
Were you on the winning team? He was on the
Second place team.
He lost to Curcio.
There was no coding.
People just really like Curcio. What they have you guys make? Or what did they want?
It was an interesting thing, but I would call it an entrepreneurial workshop. So the very first, we broke into groups. The very first thing we did is they had us draw things out of this thing and then split into like a group of 7 people, let's say, and you had to brainstorm an idea and pitch what a solution to this problem would look like. So the first thing my group had was the answer thing you were doing is it's like something for something else. So ours was it's like Fitbit, but for couch shopping is what my group had to do. So we had to come up with a solution to a problem that would be a Fitbit type thing, but for shopping for couches. So then there was a winner from each of the exercises, and then the final things were, depending on which team you were, you had to pick one of the 3 winners from the first exercise, one of the 3 winners from the second exercise, one of the 3 winners from the third exercise, and you further fleshed out that idea.
So you didn't get to be on a team of all Concordia people?
No, they randomized the team. So the final team I was on with one Concordia person. Blaine was on the team. I think Curcio was the only Concordia guy on his team, wasn't he?
Yeah, because he had 5 girls, him, and then another guy from somewhere else.
And ours was definitely better than theirs. It was garbage. Mine was like a legitimate idea.
Can't let the guy with a PhD win.
Yeah.
I mean, ours was like a legitimate idea that was architected.
Theirs was a great, legitimate idea that followed the structure of everything we've done all day. Curcio went and made a website.
Yeah, so they were impressed that he made the stupid little website. I mean, ours used real tools. Like we said, I mean, this was like using augmented reality, like place Kohler appliances in a bathroom where you could like see through walls to find out whether the plumbing you needed. So we were using machine learning, penetration through walls to see what's behind the wall, using machine learning to identify what that is. Is that a water pipe? Is that something like that? And then also using the technology to place the stuff in the room and determine. We actually linked to real APIs. Like you could actually implement it. And theirs was a stupid website. Garbage. Just garbage.
Sounds like